there exists a structural innovation capable of reducing a home's temperature by 15 degrees Fahrenheit during the peak of summer, requiring no moving components, not a single fan, and consuming not 1 watt of electrical power. While the contemporary construction sector predominantly employs mechanical HVAC systems, whose efficiency diminishes with each passing season, this novel approach transforms a building's very walls into a cooling apparatus. It's a system that harnesses the density of air and the principles of the ideal gas law to generate a constant, silent circulation of air. This ventilation purifies the atmosphere of toxins, curbs the growth of mold, and liberates individuals from their dependence on the electrical grid. Despite being the most economical cooling solution ever devised by humankind, this technology has been relegated to the sidelines by a building industry that favors hermetically sealed, plastic-sheathed structures over dwellings that genuinely possess the capacity to adapt and breathe. So, what exactly is this innovation? How does it function? And, more crucially, how can it benefit you? Let's embark on a discovery. To grasp why this technology poses a threat to the established energy paradigm, one must first comprehend the predicament it was engineered to resolve. The adoption of the solar chimney was never a matter of stylistic preference. It was an absolute necessity. The genesis of this technology can be traced back to the arid, sun-scorched plateaus of ancient Persia, particularly in cities such as Yazd. 3,000 years ago, architects faced a critical environmental challenge: how to maintain a habitable urban environment when the ambient temperature routinely surpassed 113 degrees Fahrenheit. They lacked access to electricity or chemical refrigerants. What they possessed was a profound, mathematically informed understanding of air density. They devised the badgir, a vertical masonry shaft that capitalized on the thermal inertia of dense stone. These were not mere ornamental towers. They represented the world's inaugural solar thermal engines. By exploiting the pressure differential between shaded courtyards and the sun-heated tops of the towers, they established a continuous thermal siphon. In numerous instances, these towers were integrated with qanats, subterranean water channels. The tower would draw air across the water, employing evaporative cooling to lower the air's temperature before it entered the living spaces. For centuries, this represented the global benchmark for high-performance cooling. By the 19th century, as the British Empire extended its reach into regions like India and Africa, they encountered these systems and incorporated them into colonial hospitals and barracks. The British Medical Journal documented that wards outfitted with these thermal shafts exhibited significantly lower mortality rates during outbreaks of cholera and influenza. The underlying reason was not medical intervention, but rather fundamental physics. The shafts provided a constant atmospheric renewal, expelling pathogens and moisture that flourish in stagnant air. The reason a solar chimney surpasses a mechanical fan in efficacy is not a matter of raw power, but of the physics governing the stack effect and the Bernoulli principle. To comprehend the engineering of a building that breathes, one must trace the path of the air. At its fundamental level, a solar chimney is a vertical conduit engineered to maximize solar energy absorption. It comprises a highly efficient absorber plate, typically a dark-colored metal or masonry surface, positioned behind a layer of glazing that allows for high light transmission. As solar radiation penetrates the glass, it strikes the absorber plate, where it is converted into long-wave thermal energy. According to the ideal gas law, as the temperature of the air within this shaft ascends, its density diminishes. The air becomes less dense than the surrounding atmosphere. These energized molecules begin to ascend rapidly towards the exhaust opening at the apex of the chimney. This upward movement creates a region of lower pressure at the base of the chimney. Since nature abhors a vacuum, the building is compelled to draw in air. It pulls fresh, cooler air from the lowest, most shaded part of the building, often a north-facing inlet or an underground earth tube, and draws it through the occupied spaces. Furthermore, because the system is powered by solar radiation, the velocity at which the chimney moves air is directly proportional to the heat load on the building. On a 100-degree Fahrenheit afternoon, when an air conditioning unit is straining and drawing maximum current, the temperature differential, the difference between the collector and the ambient air, is at its zenith. The chimney reaches its peak performance, circulating thousands of cubic feet of air per hour without the activation of a single mechanical component. But what occurs during the winter months? This is where the dual-mode engineering comes into play. A meticulously designed solar chimney incorporates a bypass damper. In winter, the exterior exhaust vent is sealed, and an interior return vent is opened. The ascending warm air is no longer expelled outdoors. Instead, it is recirculated back into the building's thermal mass. This effectively transforms the cooling tower into a substantial solar air heater. The performance of this atmospheric engine is governed by two principal factors: the height of the shaft and the temperature gradient. The greater the height of the shaft, the more pronounced the pressure differential, and consequently, the higher the velocity of the air. This represents the engine's displacement for your home. The efficacy of these systems is not merely anecdotal. It is substantiated by decades of bioclimatic research. In 1995, researchers at the University of Arizona conducted a comprehensive evaluation of a residential solar chimney situated in the Sonoran Desert. Their findings indicated that the system maintained an indoor temperature of 75 degrees Fahrenheit, while the external air registered a scorching 106 degrees Fahrenheit. This constitutes a 17-degree Fahrenheit reduction achieved solely through the influence of atmospheric pressure and solar heat. However, the most compelling evidence lies in the air exchange rates. The Environmental Protection Agency estimates that indoor air is frequently 2 to 5 times more polluted than outdoor air. In a modern, hermetically sealed home equipped with a conventional HVAC system, the air is largely recirculated, providing less than half an air change per hour of fresh air. This leads to the accumulation of volatile organic compounds, carbon dioxide, and moisture. A solar chimney, conversely, delivers between 8 and 12 air changes per hour of 100% fresh, filtered air. This continuous atmospheric flush effectively prevents the sick building syndrome that plagues contemporary residential construction. It is the mechanical equivalent of leaving every window in your house ajar, but without the associated security risks or the compromise of thermal regulation. From a carbon and sustainability perspective, the comparison is not even close. The manufacturing, installation, and operation of a standard 3-ton central air conditioning system over its 15-year lifespan incur an embodied carbon debt of approximately 25 tons of carbon dioxide. A solar chimney constructed from high-mass masonry, recycled aluminum, and glass achieves a carbon payback period of less than 6 months. Once the structure is erected, its operational cost is zero. It functions as a carbon-negative asset that enhances property value while simultaneously reducing operational expenses. The impact these systems have on personal energy independence is profound. A study conducted by the University of Nottingham revealed that buildings incorporating solar chimneys could reduce their overall cooling energy consumption by up to 75%. In an era of escalating energy costs and grid instability, this offers a level of security that no mechanical appliance can provide. So, why has it not been widely adopted? The answer lies in the prevalent methods of financing and regulating comfort. The contemporary building industry is structured upon a foundation of subcontracting and standardization. It is simpler for a developer to erect an inexpensive, thinly constructed, uninsulated structure and then contract an HVAC technician for approximately $5,000 to install a mechanical heating system. This plug-and-play solution necessitates no specialized architectural expertise and no integration into the building's physical footprint. Furthermore, there is the trap of energy dependence. Utility providers and manufacturers of mechanical cooling units have no vested interest in promoting a technology that never malfunctions, never requires filter replacements, and never generates a monthly bill. The prevailing regulatory framework that obstructs the integration of solar chimneys into the American building landscape is the International Residential Code. While the code does not explicitly prohibit solar chimneys, it is exclusively formulated around ASHRAE 62.2 standards, which prioritize mechanical ventilation. Because a solar chimney is a passive system, its performance fluctuates based on solar intensity. It falls into a regulatory gray area. It lacks a UL listing or an Energy Star certification from a factory because it is not a manufactured product, but rather an architectural feature. Most local building inspectors will, in practice, mandate a mechanical backup system, thereby doubling the construction costs and compelling homeowners to acquire an appliance they do not truly need. This constitutes a de facto prohibition through bureaucratic processes. We are led to believe that active systems, those employing compressors and refrigerants, are modern, while passive systems like chimneys are antiquated. However, in reality, the mechanical appliance represents the primitive solution. It relies on brute force, substantial energy consumption, and intricate components prone to failure. The chimney, in contrast, is the sophisticated solution. It leverages an elegant, enduring understanding of universal physical laws. It represents a cycle of planned obsolescence, compelling you to purchase a device engineered for failure to rectify a dwelling also designed to falter. If you wish to incorporate an atmospheric engine into your own residence, here is a practical outline of how that can be achieved. There are two primary avenues for implementing this technology. For an existing dwelling, the most efficient approach involves a wall-mounted solar chimney. This is essentially an insulated enclosure affixed to a south-facing exterior wall. To construct one, you will require an absorber plate coated with a selective surface paint, a material that absorbs 95% of solar radiation while exhibiting low emissivity, thus minimizing heat dissipation back through the glazing. Subsequently, this is covered with low emissivity glass to trap the heat within the shaft. For a 500 square foot living space, an absorber area of approximately 20 square feet is recommended. The cost for a do-it-yourself installation ranges between $300 and $700, depending on the materials chosen, such as UV-stabilized polycarbonate and high-temperature silicone. You will need to create two 6-inch openings in your wall, one near the floor and another near the ceiling, and then allow the principles of physics to take effect. For new construction, the optimal strategy involves designing the structure as a purpose-built thermal exhaust engine. Unlike a retrofit, a new build allows for precise calculation of the building's neutral pressure plane to maximize the stack effect. This strategy entails integrating vertical shafts, ideally ranging from 20 to 33 feet in height, into the south-facing thermal mass of the residence. These shafts must be lined with a spectrally selective absorber plate and protected by high transmittance, low iron glazing to prevent thermal re-radiation. By positioning the air intake at the lowest, most shaded point of the structure, the chimney establishes a continuous pressure differential. This compels the house to draw in geothermally cooled air at the ground level while simultaneously expelling the buoyant hot air through roof-level vents. This results in a 0-watt, high-volume air exchange system capable of providing 8 to 12 fresh air changes per hour, thereby obviating the need for a mechanical compressor. And if your objective is to achieve a truly radical level of self-sufficiency, you can complement your solar chimney with an earth tube. This involves burying a 100-foot length of 6-inch diameter PVC or clay pipe 6 feet underground, where the temperature remains a consistent 54 degrees Fahrenheit year-round. The solar chimney provides the necessary suction to draw fresh air through this pipe. By the time the air reaches your living area, it has been geothermally cooled to 70 degrees Fahrenheit. This effectively functions as a 0-watt air conditioner, operational even during a complete grid failure. Maintenance is the final consideration. Due to the absence of moving parts, refrigerants, or motors, the system is designed for perpetual operation. An annual inspection of the intake filters to ensure unimpeded airflow and a cleaning of the glazing to maximize solar transmittance are the sole requirements. Unlike an air conditioning unit, which necessitates an annual service call costing approximately $200, a solar chimney functions as an intrinsic, permanent component of the home. The solar chimney represents a 3,000-year-old solution to a 21st century challenge. By allowing the principles of physics to operate, it can transform your home into a silent, self-regulating air circulation system, independent of the grid, utility companies, or the cycle of obsolescence that characterizes modern housing. Much of the subject matter covered on this channel was almost forgotten, not due to its obsolescence, but because the industry deemed simplicity insufficiently profitable. If the rediscovery of the lost arts of self-reliance and high-performance construction holds significance for you, then subscribing and sharing is the most straightforward way to ensure such knowledge continues to be disseminated. In this presentation, we have explored the solar chimney, which harnesses solar energy to facilitate air movement. However, if you are interested in observing the application of this same thermal mass principle to a wall that converts solar energy into heat using only the